Hello, my name is Michael Loster, and in this short talk, I would like to present our work on few-shot knowledge validation using rules. From virtual assistants like Alexa or Siri to risk assessment of financial institutions, the need for high-quality knowledge graphs is growing steadily. Since the automatic or semi-automatic construction of large knowledge graphs is a challenging task, the creation of completely error-free knowledge graphs can often not be guaranteed. Therefore, finding and eliminating possible errors in the knowledge graph represents an important task. Here, logical rules, which are derived from the knowledge graph itself by systems such as ANY or Rudik, can be used to improve its data quality. These are typically rules like the ones shown here, which states that if A is married to B and B lives in C, then A must live in C as well. The application of such rules allows us to add missing, remove violating, or fix incorrect entries in the knowledge graph. However, a closer look at the rule generation process reveals the following problem. If the knowledge graph is of low data quality, how can we have confidence in the correctness of the generated rules? Based on this question, the need arises to evaluate the data quality of a rule independently of the quality of the underlying knowledge graph. To address this problem, we present COLT, a framework for interactively assessing the quality of logic rules. The general idea behind COLT is to train a model on a subset of the implied facts of a rule whose quality is to be assessed. COLT incorporates user feedback into the training process to counteract poor knowledge graph quality. The learned model is ultimately used to derive a conclusion about the quality of the rule in question. Let's take a closer look at the COLT framework. We start with a rule whose quality we want to evaluate. In this case, we selected a rule that states if A acted in B and A created B, then A has produced B as well. Executing this rule on the knowledge graph yields all triples that satisfy the rule. In this concrete example, we would get facts such as Robin Williams produced Mrs. Doubtfire. But is this conclusion correct? To figure this out, we pass the fact to a domain expert who evaluates the correctness of the received fact. Next, the subject and object of the evaluated fact are transformed into a 200-dimensional graph embedding by means of an embedding approach such as TransE or, as in our case, Hyper. This translation is performed as a knowledge graph. Embedding implicitly captures structural and semantic information of the knowledge graph and represents a more informative representation of the fact components. The generated vector representations of subject and object are then concatenated and added to the training set. This data set, consisting of subject-object combinations and their associated truth values, is then used to train a model capable of assessing whether a given fact of a rule is correct or incorrect. Once the model is trained, it can be used to re-evaluate the confidence values of the remaining facts, which in turn can be used to select the next facts to be evaluated. This process continues until either all facts have been evaluated or a designated budget is depleted. Next, we take a look at the models that allow us to learn the truth values of a fact. Our first model is called COLT-MC and represents a greedy baseline based on maximum coverage. In this image, each point represents the previously generated vector representation of a fact. Essentially, it can be thought of as a one nearest neighbor classifier that compares a selected fact to all previously evaluated facts, determines its nearest neighbor by means of a chosen similarity measure, and assigns the same label as its neighbor to the selected data point. COLT-MC determines the similarity of two facts based on their cosine similarity. Thus, it uses a fixed similarity measure and relies completely on the correctness of the determined similarity. Our second model is named COLT-GP as it is based on Gaussian processes. Unlike COLT-MC, it learns a similarity measure between individual facts and makes predictions on a scale from 0 to 1. Given a set of labeled facts, it learns to estimate the probability that a fact is correct or incorrect. Here, a predicted value of 0 indicates that a fact is incorrect, while a value of 1 implies that a fact is correct. In addition to the prediction itself, the model also provides a quantification of its uncertainty in its predictions. This property allows us to use efficient sampling strategies, which we will introduce in a minute. For example, it might make more sense to present the model with a data point where its uncertainty is quite high, rather than a data point like this one, where the model is very confident in its predictions. To circumvent traditional limitations of Gaussian processes, we leverage deep kernel learning, which combines the strengths of Gaussian processes and neural networks in one unified model. The model consists of two main components, a fully connected neural network and a Gaussian process layer. Deep kernel learning refers to the fact that the kernel function required by the Gaussian process is learned by a neural network. The neural network part of the model effectively performs a dimensionality reduction, transforming the n-dimensional fact representations into a low-dimensional vector representation. The Gaussian process layer receives this low-dimensional representation as its input and yields the final prediction y. As mentioned before, a crucial part of the framework is how unlabeled facts that are assigned to a user for evaluation. To this end, we evaluate three different selection strategies: random, maximum uncertainty, and GPUCB. Random refers to the simplest of the three selection strategies in which unlabeled facts are selected at random. Maximum uncertainty sampling uses the model itself to assess how valuable the labeling of each data point is. Concretely, this sampling strategy uses the model's uncertainty on unlabeled data points. The GPUCB strategy tries to find a balance between exploring the function space by selecting data points with high uncertainty or exploiting the function space by selecting data points that it is fairly confident about the classification outcome. We use Yago as the basis for creating our dataset. As a first step, we generate rules by running Amy and Rudink on Yago, deriving both positive and negative rules. In total, this resulted in 1,517 generated rules. To keep the following annotation process within manageable scope, we selected 26 rules out of 589 rules that generated less than 5,500 facts. This selection was made based on a number of properties, such as the number of atoms in the rule, the facts it produces, or the rule's confidence value as determined by Amy or Rudink. We then manually annotated all facts generated by these 26 rules according to their correctness. This ultimately results in a dataset consisting of 23,324 annotated facts. As they are ultimately responsible for composing the training set, the use sampling strategies play a crucial role in the COLD framework. Thus, we examined the effect of the different selection strategies on our COLD-GP model. The plots show how different sampling strategies affect the precision, recall, and F-measure of COLD-GP. We conducted the experiment by using the respective sampling strategy to select a continuously growing set of training data. We then trained the COLD-GP model on the selected training set and made a prediction on all remaining facts, including the previously selected ones. As expected, the random sampling strategy turns out to be the strategy with the worst performance. GPUCB performs better, but requires up to 6% of training data to achieve a complete competitive precision value of 77%. Regardless of the number of instances used, GPUCB remains below the F-measure of the maximum uncertainty strategy. Overall, the maximum uncertainty strategy provides the best results in terms of F-measure as it outperforms the other two strategies at all times. This is why we use the maximum uncertainty strategy in all following experiments. Next, we examine how COLD-GP compares to our COLD-MC approach and two active learning baselines. To this end, we train CaltGP on we trained CaltGP and all competing approaches on an increasing amount of training data, resulting in the 3 performance graphs reporting on precision, recall, and F measure of each approach. As the plots show, both active learning strategies fall behind the CaltGP and CaltMC approaches rather quickly, suggesting that neither model possesses sufficient capacity to cope with the complexity of the problem. After using 15 to 20% of all training instances, their performance stagnates between 80 to 84% F measure. While CaltMC performs better than the traditional active learning approaches, it shows slower growth than CaltGP and has a near linear growth between 12% and 100% of the training data in the F-score plot. In contrast, CaltGP outperforms all competing approaches in all performance metrics and inhibits a faster growth rate than CaltMC. As a result, CaltGP already achieves an F measure between 75 to 80%, while using only 5 to 10% of the training data. Looking at the performance of all 4 approaches, we conclude that it is not sufficient to rely solely on fixed similarity measures, as in the case of CaltMC, or on traditional active learning strategies. In our last experiment, we compare the rule confidence estimation of CaltGP with the data-driven standard confidence measure, SCF, as it is reported by AMY. The solid red line shown in the chart represents the average SCF estimate, which is 19.6% away from the correct confidence value. To calculate the estimation error of CaltGP, we use an increasing number of instances to train a model for each rule that generates at least 100 instances. We report the average error of these models, which is represented by the blue line. We observed that CaltGP is more accurate at estimating the average rule confidence than AMY's SCF estimate from the start. As we proceed, we find that 10 to 20 training instances are sufficient to achieve an average estimate confidence error of 12.9 to 10.8%. As the number of training data increases, the estimation error further decreases and reaches its lowest value of 4.5% with 100 training instances. In summary, CALT represents an effective framework for the interactive quality assessment of logic rules. Its most expressive model, CaltGP, makes use of knowledge graph embeddings and user feedback to overcome data quality issues in the knowledge graph. It attains a 10% error in confidence estimation within 20 user interactions and 75% F measure in predicting a rule's quality by using only 5% of all labeled training instances. We release our dataset consisting of 26 rules and roughly 23,000 annotated facts to the community for further research. Possible future research includes the extension of the framework to allow the characteristics of multiple rules to be learned, as well as the ability to generate refined rules by utilizing CALT. With this, I would like to conclude this talk and thank everyone for their attention.